Hello. Glad to be here to present today about the scheduling priorities and FreeBSD. Thank you for coming and attending this presentation. It's actually my first presentation to EuroBSDCon, so I thought I'll do a few slides about myself, but very quickly. I'm French. I've been in the IT sector for a long time. I love some kind of weird and old languages. I do all kind of stuff, such as developing and architecture in different business sectors. And my involvement with the BSD community, actually with FreeBSD, up to now, it has been for a long time, actually, but not really in public. In public, it has only been for a few years. And actually now I'm working full-time on FreeBSD, as I am a FreeBSD Foundation contractor since last September, working on different topics. We're going to see that. So, just to mention a few of the work I've been doing during the last year, which is not connected to that presentation. There are several things. Some are small tasks, other are more critical bug fixing, or rather reporting those bug fixes to different branches, but then trying to have some background work about the problems we have in different areas. And actually, I mentioned here UnionFS because as part of the contract with the FreeBSD Foundation, I'm supposed to work on UnionFS, on revamping it, so it has not really started. I've been, for now, reviewing batches of changes by other people, which are doing quite nice work, but it should normally start in a few while. So coming back to the topic today, the project goals for this project, which is a kind of background project, is to try to fix scheduling APIs bugs, to try to decouple the implementation and interfaces, because actually we had lots of duplication, or code duplication, and actually not exact duplication. It's also to work on better POSIX compliance where we can, and extend the usefulness, because we have some quite powerful APIs that could be used for a number of tasks, and today there are some bugs or there are some difficulties in using them. So this presentation has an accompanying paper, which is, in fact, was done for the Asia BSD conference at the beginning of the year. So, and in this paper, you can find a description of the API, of the different APIs we have in FreeBSD, which are rtprio, which was the first one, and I should say the kind of native one, and then the POSIX one. So if you want to use these APIs or see how they work, I advise you to read that paper. I've put the URL at the end of the presentation. So I'm not here going to survey these APIs exhaustively. I've tried to focus on a few different points that I hope are interesting, because in this project there is also a lot of menial work, a lot of refactorings, and that's more or less boring stuff to present. So I'm trying to present, I hope, what should be the most interesting to you. So this talk will be, there are two parts. I'll just speak a little bit about the background of scheduling, with not too many details, because it can be a full talk on its own, and just explain a little bit what you can do with these interfaces. And then we'll see some of the changes I've been going through during this project. So let's start with the background. So scheduling, I assume that you know more or less what it is, but it's a very small summary. Actually, you have threads that you want to run. Some are in runnable state, and it's the business of the system, because it manages the hardware, to decide where you are going to put the different threads and execute them. And also for which duration, because you don't want some thread to starve the whole system. So at some point, you will decide that, okay, this thread has run enough. It has exhausted its quantum. So in this example, it's T2, for example. Then we will deschedule it to put something else on top. And to do that, actually, classical way of doing that is using multi-level queues or multi-level feedback queues. The multi-level queue, it's kind of queue like that. You have different priority levels. Let's say that here it's the most important priority, and here the smallest one. And you have several threads in those different queues, and you schedule them based on, you choose the one which has the highest priority. So here in this example, that would be T1. But, and that's the problem, is that that explains a little bit how it works in real time, because you have these different priorities, you assign one, but then that means that each time you have a thread in 0 priority, it is going to be executed, no matter what you have on the system aside from that. So that's why there was this refinement quite quickly for time-sharing processes. It's the feedback queue. And actually, the feedback is that if you're running too long at some priority, we are going to degrade your priority so that we can let the other threads run as well. So here, if T1 has exhausted its quantum, it's going to come back in the queue, but at some lower priority. So here, and so then we'll take T8. Let's say that T8 has ended. And next time that we execute T1, also we are going to move it to the right here. And at some point, we will be able to execute these 2 threads that are waiting there. That's really the archetypal mechanism to deal with thread scheduling, at least in the old days. And the BSDs have been based on that. So FreeBSD internal model is quite close to that. There are 3 selection policies. The real-time one, it's a multi-level queue. So that's, you assign fixed priorities. You choose the thread with highest one. It's a fixed system. Then you have the timeshare part. It's a feedback queue, as I just explained, although it leaves out lots of details. And the idle time is a multi-level queue as the real-time one, except that the threads there are less priority than timeshare. So there are basically, so what I've just presented is the internal model. But, especially in the old days, all the interfaces you get are quite close to that internal model. That's why I wanted to present it first. So for rtprio, it's an interface that comes from HPUX, but which was modified for FreeBSD. Basically, at start, there was only one system call, rtprio. And then some years later, we added another one for threads. It's very simple. You can set or retrieve attributes. And the settings you have access to, basically, you have 2 attributes there, the scheduling type and the priority within that class. So here I'm talking about functional classes. It's different than what I showed before. Before it was how the system selects internally the different threads. Here you are more saying, okay, I want that kind of behavior. So there are several possible types. In fact, I've put in red the current behavior, and then I have another slide with the new behavior or expected behavior after the changes. For example, if we take interrupt threads, fortunately, you cannot change their priority. It's kind of system critical. But if you try to get the setting, you'll get random values. And basically, it's an initialized memory read. So that's a bit annoying and has to be fixed. Here, we have a range, a fixed range, but there's a problem with it that we'll talk about later in the presentation. And for kernel threads, the system reports, okay, it's normal priority, which is not, actually, and priority 0 for all these threads. So well, what I would like to come to is to have, here it will stay implementation dependent, but at least we'll get real internal value. And for kernel threads, it will be the same with a dedicated class. So that's just for reporting. that part. And the second part, after, with less priority, I have time-sharing threads. Currently, the range here is implementation dependent. Actually, has changed as of FreeBSD 14. And even worse, it's dynamic. That means that if you constantly request the current settings, you're going to get different values. So that's kind of very strange. And it's obviously, from an administrator point of view, you don't really understand what's going on and what you can do with that. And idle threads, it's a kind of mirror of real-time threads. So what I would like to do, and I explained that a little bit later, I would like to have a fixed range here. And these values, of course, are not random. They correspond to nice values, which is one of the possibilities. It's not the only one. And I would like to fix also the caveat I'm going to talk about for idle threads. So the POSIX interface now, it's very similar, but there are some differences. The priority levels are reversed, so if you have a higher number in your class, actually you have more priority, but in rtprio, it's the opposite. So you really have to be careful depending on which interface you're using. There is also, according to the standard, we should provide an absolute priority scale, which means that the different priorities you have per class, actually they are not per class, they are global, and they should be globally comparable. That is to say, for example, if I choose, if I have real-time process threads, let's say having the highest range in a byte, let's say between 200 and 256, that means that if I have time-sharing threads, they must have a range assigned that is lesser than this one. You cannot have different policies with the same values, at least in theory. That's what the standard mandates. And also there is some kind of caveat because actually process and thread scheduling settings are not the same, not necessarily the same, but I'm going to go back to that. The only thing that is really the same as the rtprio is that all priorities are positive. So that's the theory. And to check, I've done a simple reality check on that to see which properties are important to have for compatibility and which others are not really important. So the reverse priority levels, almost everybody complies. But HPUnix, no, curiously. With non-negative priority numbers, it's also okay. We only have 2 outliers there. But then things get a little bit fuzzy because for absolute priority scale, actually, there are none of the open source current Unix systems that really abide by that for lots of reasons, mostly historical, I guess. And about the process thread scheduling settings, actually all these systems we used in FreeBSD, we used to support the process contention scope, which means that the different threads in one process, they compete against each other to get CPU time, but then it's kind of a hierarchical model, and then the processes themselves will compete for CPU. But it has not been the case for a long time now in FreeBSD, since abandoning the M2N threading library, KAC and. 7.2? 7.2? I'm not sure, maybe around that time, I would say. So the trick is that according to the standard, now all these systems would support only system contention scope, but that means that according to the standard, that if you use the API that are targeted to processes and not threads, those targeted to processes, they are not supposed to have any effect. They shouldn't do anything. And in fact, no system complies, actually, except OpenBSD because they don't implement that. But that's the only, all systems do not comply to that. They actually, because these APIs are quite useful, and it would be a waste not to use them, not to implement them in meaningful ways. But there are different implementations. So that was a quick tour about scheduling policies and the different APIs and what you can do with it. Yeah, I didn't describe exactly real time, but with the multi-level queue, I hope that's clear what's these classes are doing. So some of the impacting changes, although some of them are still under question, I would say. Yeah, so I said that for the time sharing threads, we have dynamic levels. That is, if I try to set, for example, the level for the shell here to 10, okay, this is the reporting I wrote. This is obtained through the POSIX API, and this is obtained to the rtprio API. So you see that there is a discrepancy that shouldn't be there, or at least it should be clear why there is a discrepancy. And then if you query that priority over time quite quickly, you see that, okay, quickly it's as if you didn't specify anything. So it's mostly as if that was ignored. Then you get 0, and then, which I noticed the first time by chance, if you repeat that invocation quite quickly, you'll begin to see numbers increasing, which was kind of strange at first. But after analysis, it comes from the fact that you're using more CPU time that is accounted to the shell. And so the scheduler is going to increase that priority because it's dynamic. And so you're getting these increase in numbers. So you'll see it's not really useful for administrators because you have a setting, it doesn't really work in any meaningful way. And even for reporting, it's great to have internal reporting, but it's mostly for developers, not really for administrators. So there were also other problems with that. The different levels are tied to internal priority levels. So this is something which is kind of an implementation detail. And we have these inconsistencies I just showed when you query the different interfaces. Although internally, in the end, the code is the same, or some routines are the same. So that's really weird. So I'd like to switch to fixed values. So which ones? Actually, there are several answers possible. The Linux answer is saying, okay, there is only one level. But it's not the full answer, because actually they have nice values per thread, because they modeled thread through processes, and nice values were initially per process. So that was my idea here. We use nice values because these at least have some kind of meaning, so fixed meaning that is not going to change across different versions, or then the meaning of each nice value also is not fixed, but at least it's something stable that the administrator could reason about. So we would need them per thread, contrary to what we're doing now. And then this raises a number of questions. Are we going to still be POSIX compliant? Well, we are not going to be compliant to absolute priority levels, because the big thing here is that if you read carefully the standard, I think the most probable interpretation is that these different levels, these are levels as in multi-level queue I showed at the beginning, which means that if you set some thread to a high value, then it's never going to run if there are threads with lower priority. And obviously, that's not what you want when you're doing time sharing. That's exactly the opposite. So that means that we'll probably give up on that. But as I showed, we wouldn't be the first ones, actually. And then we have to have a mapping to process nice value, because we have to maintain that invariant, which is mandated by the standard. And there are also interesting effects that we could have with existing applications. Actually, not many applications are using the POSIX API. I've done a quick survey. There are some which are using it, but I think it's under compile options, or even you have to use some special runtime options. You have Ruby, VLC, for example, Handbrake. These are the kind of software doing video, or usually doing video or audio, that we use them, and they are not using them properly. So anyway, this will require fixing, but it's a separate, would say separate project. Okay, so I wanted to talk a little bit very quickly about the scheduling privileges. So effectively, if you are able to run threads in the real-time class, these threads have more priority than the regular kernel threads. So you can easily deadlock a machine if you're running something which is an endless loop or taking too much resources. So obviously, this has to be controlled. So traditionally, that was reserved to root. In FreeBSD, we have this privilege API that can actually allow to grant several privileges to some users or to some processes through the Mac framework. So it's quite powerful. I'm not going to describe it here. But I'm just listing the list of scheduling privileges we have today. It's a bit strange, actually, because some of them you probably can figure out quite easily what they're doing, but some it's a bit difficult. And actually, some of them are not used at all in the code. They are just declared, but never checked. And some are checked in some code paths, some others in other ones, but they all end up in the same code in the end. So that means that you can bypass one if you have the other. So that's a security problem. So my goal is to get rid of these ones and to keep only the essential one. This is for real time. There is a special privilege for idle time priority because it was believed that you could deadlock your machine as well using idle priority stuff. For example, if your idle priority takes a resource, it doesn't have time to free it, and then you have lots of processes running that would like to access the same resource, so you could have a deadlock problem. Actually, I think that for lots of complicated reasons, today it's not possible if you don't tweak the Yule scheduler too much. I don't think it's possible that this can happen, but still it's historical. And for a more practical point of view, if you want to use them, for example, you would like to put some background compilation into idle time, currently, so you have to be root, or you can use Mac priority, which actually grants the proper privileges based on belonging to some Unix group. So it's kind of useful for if you're doing sound processing, or even for the real-time part. But for the idle time part, it's great for compilation, for example, or some background stuff that you don't really care about and don't want to disturb your other work. So I said in the first part that there was a caveat with real-time priorities. Now I'm going to explain what it is. So this is again from the standard. So we should have at least 32 priorities, and it's very clear in the standard that each level is different and has to be treated differently. So at first I was saying I didn't notice that there was a problem because we have this constant, and I added some more checks about that to be sure that we're not going to reduce it. So everything seemed okay, superficially. But in fact, there is a problem, because we are doing internally priority levels conflation. So we have the FreeBSD run queue. The run queue is the essential brick to actually implement the multi-level queue and the multi-level feedback queue I just talked about at the beginning. But the trick is that it only has 64 different levels, although you have internally, we have 256 different levels, priority levels. So obviously you have to have some mapping, and the mapping is very simple. But that means that effectively for internal priorities, if you have 4 of them that are going into the same bucket. And all threads on the single queue are treated the same. It's basically what I showed in the drawings at the beginning. And to add to that, what we are doing is that for the different levels of rtprio real time, so this is what the user sees, actually, the interface, each level is mapped one-to-one to some internal priorities, to some reduced range, obviously, but one-to-one. So effectively, you get that 4 consecutive levels are mapped to the same queue and are treated the same. So we are not compliant. So there are, again, several ways to fix that. I tried more. I wouldn't say it's a moonshot, but I just didn't want to try to fiddle with all the internal mappings we were doing. I had enough of that, so I decided, okay, we should just use a big run queue, which corresponds one-to-one with the internal priorities we have. And it solves that problem, but actually introduced another one. Yeah, in fact, I will explain. So Yule is the default scheduler and has been in FreeBSD for more than 15 years, I would say. So what I said before is not exactly true. It's true for the old scheduler, for BSD. But for Yule, we have 3 run queues, actually. We had three run queues. And there were 1 run queue per selection policy. So as I showed at the beginning, real-time, time-sharing selection policy, and idle time. I hope you, there are lots of different terms that are almost the same. I hope you're not completely lost about that. Here, I'm really talking about how the systems internally choose the next thread to run. Because as I said, in the real-time policy, you have real-time threads, user-land real-time threads, but you also have kernel threads and interactive threads for Yule. So the time-sharing threads, they are divided into 2 classes by Yule. The first one goes into the real-time selection policy, and but after kernel threads, contrary to real-time user threads. And we have the batch ones, so they are not deemed interactive, and only these ones go into the time-sharing selection policy. So internally, we have a range of 88 priority values, but since we have a dedicated run queue for it, that means that we only have 64 levels. So we have to do some mapping. And computation is based, the computation of the priority value is done by the scheduler, and is based on the CPU usage and the nice part, the nice value part. But if you're doing that and you just keep the usual selection, that is to say, you take the thread in the queue that has the lowest value, corresponding to the priority with lowest integer value, then you're going to have all the usual problems, and you're not really doing time sharing. So in order to circumvent that, you'll use NQ and DQ offsets. So we are not going in the run queue, we are not going to insert, for example, a thread with priority 0 in that range, so 136. We are not going to map it to the level 0 anytime. This is going to change, actually. And this is what is called the calendar queue. This is a mechanism to prevent starvation. Really, the real reason for doing that is trying to keep the 4BSD's decay, priority decays we have for fairness, and to have that, but stay big O1 in the number of threads. So instead of working the whole list of threads and changing their priority one-to-one, because that can cost a lot, instead of that, you're just changing the reference point. That's basically the idea behind the calendar queue. I've got a few drawings just to show how it works. So let's assume for a moment that it's only the time-sharing queue here. And we have 2 heads, the DQ and NQ head. And as usual, the highest priority is on the left with lowest integers. So at each tick, we move the NQ head. But the two heads are in lockstep. That is to say, the NQ head cannot move too far from the DQ head. Actually, initially, it was only one gap maximum. So this corresponds to time passing. And then let's say that we were running some T2 threads, and now the scheduler determines that based on the CPU ratio, it has a priority of 2. We are not going to, and here we also assume for simplicity that there is a one-to-one mapping. So if I have priority 2, I should go normally to queue number 2. But I'm not going to go into queue number 2. I'm going to actually go into queue number 3 because I have this offset. The enqueue head works as an offset. So I'll get here. And since the DQ head is still there, the starting point is here, so we consider that this queue has the threads with highest priority. So we are going to dequeue these ones and execute them. And once it's done, when the queue is completely empty, I can actually move the dequeue head towards the enqueue head, allowing the enqueue head to move again. And what's the effect of that is that, for example, now, let's say that the thread we were running, which could be T8, for example, creates a new thread that has priority 4. And then I'm going to enqueue that thread here in 6, because now my head is here at 2. So what happens is that, so T2, I will execute T2. But, oh, sorry, there are some drawings missing maybe. But that means that T4 will be executed after T10 and T17, for example. And we can assume that these were inserted with priority 5 when the enqueue head was at 0. So basically, that means that, OK, that thread has a higher priority, but in the end, we will execute it after these ones, just because time has passed. And this is the way we actually implement the anti-starvation mechanism. And this mechanism is quite sensitive to the timing, because you only move the enqueue head based on time, on ticks, actually. So with all the changes I talked about, now we have only one run queue. It's kind of implementation detail. But what has changed is that we have more values in the time sharing range now for a variety of reasons, because, for example, Jeff, the initial author of EULA, wanted more time sharing levels. And actually, we were able to free some because we are not conflating them anymore. So there were some kind of tricks in the kernel saying, OK, for this kernel thread, I want this priority. And for this other, I want this plus 4, just to avoid the conflation I mentioned. So now we have a lot more values. So we could have kept exactly the same number of values. But I wanted to experiment with using the full range. And the trick is that if we want to preserve the exact anti-starvation mechanism we have now, we actually have to preserve several things. We have to preserve actually 2 things. First, the ratio of contribution between the NICE contribution and the CPU usage contribution that are used to compute the actual priority by the scheduler. We have to preserve that. If not, that means that the NICE values are going to have different effects. And for starvation, we must also ensure that we are going to have the same span in the same amount of time. So that means that initially, we had to return to the same position after 64 ticks, because there were only 64 queues in the run queue, dedicated run queue. Here, we have a variable number of queue, which is configurable, by the way, now. And to regain that property, actually, we can have, it's approximate, it's really close. So we decided to change the rate of advances to the head. And the result of that is that if we test 2 threads with different NICE values on the same CPU, and we compare the CPU usage of the highest priority thread for the 2 different, for before and after the changes, then we see that we are able to approximately preserve the existing behavior. Whoa. And so we approximately preserve it, which was a problem with the initial series of patch. I've been discussing a lot with Jeff about what we should do next for EULA, but we didn't want to conflate that with some other changes. And wanted to have things separate because it's already quite a big change. So we seem to be good on that front. And then, unfortunately, it seems to be kind of usual in this project. You change something here, and then it changes something else, and then something else, and then something else. But there, it's not exactly the same case. I just noticed this. So if you have two different processes, two threads, one with minus 20, or with corresponding process having nice value of minus 20, it will only get 67% of the CPU, which is quite astonishing because it's the whole range of nice values here. So Jeff was not really aware of that problem. And so that's, it seems that we have other things to fix and to work on. So that will be continued. So, okay, I'm doing quickly because it's kind of a big project with big changes. Not everything, as I said, is really interesting to present, but there are several stuff. Actually, I've also tried to have all these changes in the Linux later as well, so there will be fixes in this area as well. So the work I have in progress is changing the priority levels for a time-sharing part, at least for the rtprio interface. I'm just wondering if it's a good idea to do that for POSIX for some of the reasons I explained. We are not going to be compliant. We are already not really in this area, so is it really a problem? I think it depends mostly on how the different applications use that and if there are impacts or not. I don't think there will be, but this has to be tested with experience and other tests. I would like also to allow some kernel threads to run in the time-sharing selection policy, especially for the ones that consume a lot of CPU, because that can cause lags and jitter. I have observed that on several boxes with Jelly, for example. And although it seems, if you look at the code, it seems that it's the case already, it's not. If you analyze it correctly, you'll see that, in fact, it's not the case. I would like to have some better priority reporting as well, probably in PS and top. Probably this is going to be controversial or not, I don't know, because I think that showing the internal priority does not have much value for the administrator. It can be discussed, but because you can compare them for sure, but the raw value, you don't really know what it means. So I'm not completely sure about doing that or not. I would like to adopt, it's kind of easy, or not that easy internally, but to adopt scat batch from Linux, which is saying, okay, I have something in time sharing, but I don't want it to be interactive, even if the scheduler has the impression based on behavior that it should be interactive, but no, it's not. It's something that should stay in the background, more or less. And I would like to fix the nice values effect. So we are discussing with Jeff about how to do that without too much disruptions, although I'm not sure it's actually possible, but we'll see. Some code status. There are currently two big series of patches. There is one, so the 256Q, which seems to be nearing completion after the recovering the anti-starvation behavior. We will see with Jeff, but I hope that this one can be committed quite soon. This one is still more a work in progress because there are lots of plumbing stuff to change, so it's really a long part. But I would like to have all this in FreeBSD 15, or by then, having had reviews, comments. Maybe there are some things that I presented that won't make it because people really don't want that. It's not completely. There are things that seem to be quite open still. And some possible future work, hybrid scheduling, because we have that in CPUs on new laptops. It's a complex, really a complex topic, but probably we can have some simple policies to start with that could be effective. Other schedulers, because ULE was based on several assumptions, such as we will have so many threads that we cannot be dependent on the number of threads to select some next thread to run. In practice, it proved not really completely true, and actually in Linux, the last two schedulers are not big O1. They are in log n, so, and it doesn't seem to matter much. And this could maybe enable some flexibility because the current mechanisms, they are quite rigid. There are a few parameters, but they interact in sometimes very strange ways. So maybe we should explore some alternatives there. I would like also to have some per process priority limit. This requirement comes from guys doing audio stuff on FreeBSD. It would be nice to have, and maybe some process mitigations, so some runaway processes mitigations when you have something in real time that goes completely mad. But we'll see. That will be more of nice to have, and there are already lots of things to do. So, okay, so it seems it's the end, and I put there all the different URLs that could be of interest. I will post the slide just after the conference so that you can actually click on links. This is the paper is on papers.freebsd.org. If you don't know that site, it's really nice because you can find all the papers of all the past conferences and the different code stuff that you can find. And I think that's all. And I welcome your feedback and questions, and now or later, because it's kind of complex subject. So there are things that maybe you'll figure out later and want to talk about later. So anyway, I'm available.
I'm interested in actual hard real-time applications with FreeBSD. Is there any roadmap towards that? Like, I think the story is we can't preempt system calls.
Yeah. No, hard real-time, yeah. At
Like
least to my knowledge.
Linux's preempt RT or something?
Yeah, it has never been on the roadmap, to my knowledge. But hard real-time, no. Soft real-time, yes, but.
So what's then the main use case for rtprio?
Oh, for rtprio, it's mostly when you want to do live sound or video processing.
Yeah.
That's basically all the use case we have.
Higher priorities, basically.
Sorry?
You need a bit higher priorities.
Yeah, or you prefer because, yeah,